we're going to revisit the CRC, the cyclic redundancy check. Why? Because it's a really cool application for those linear feedback shift registers we've been talking about. Off and on throughout this series, we've been talking about error detection and error correction. Let's assume that I have two letters that I want to send. Two? Why two? Because if I started getting longer strings, I wouldn't have enough room on this board. But let's talk about the H, which in Unicode would be 01001000, and a lowercase I, which would be 011010001. Now, if we were to use a datasum-based checksum, what that means is that we are going to add these two numbers together. So we got 1001101, and we get a result of B1 in hexadecimal. That datasum, we can manipulate it around. We can either have a ones complement or a twos complement in order to check it on the receiving end. The problem is that each one of these bits represents a power of 2 position. So if I happen to have a bit flip from a 1 to a 0 or a 0 to a 1, let's say that this least significant bit of the H turned to a 1, what that's going to give us is going to give us a capital I, and this least significant bit of the lowercase I, that turns to a 0, that's going to give us a lowercase h. Not the string we were looking for. But if you add those two together, you'll notice you'll still get that same sum, the B1. So what the goal of the CRC was, and we've talked about this before, the goal of the CRC was, instead of having these as individual numbers where each one of these represents a power of 2 from the 2 to the 0 up to the 2 to the 7th in this case when sending bytes, we're going to actually take all of those bits, those two values. I'm going to go ahead and put the original value for the H there, and then the original value for the I, and we're going to put them together into one long number. And now what we've got is individual powers of 2. If any one bit flips, we get a change in a power of 2 that is unique to that particular bit position. Now, the problem is when we're trying to figure out an error correction scheme for this, what the CRC did, and we talked about this in a previous video, was it said, we're going to take the modulo of that particular value. Not really the modulo, it's kind of, there are reasons why the modulo didn't work so well, but we're going to take the modulo for this and use that as the checksum. And the modulo is a kind of a hash function where if any one of the bits changed, we were going to get a kind of a randomish, a very different change in that checksum than we would have gotten if a similar bit change happened in another position. Let's go ahead and do a demonstration of how this might work. When we do a long division, like the good old days, what we did was we took our value, and I'm going to use that same value that I was talking about before where I have the H, and then I have the lowercase I. And if I take that value and do a long division, and I'm going to have a divisor, I'm just going to come up with a divisor. How about 10011011? All right. So what am I going to do? Well, the deal is with a normal long division, even in binary, is I have to start grabbing enough bits from my dividend so that my divisor is smaller than the number of bits that I've grabbed. So in this case, if I grab the first 8 bits, notice that I've got a 0 starting here, a 1 here. This value is clearly, this much is clearly not as big as the divisor is. So I grab another bit. Well, it turns out 10010000 is still smaller. So that would not still be large enough. So I'd have to grab yet another bit. And in this case, these 9 significant digits, drop the leading 0, those 9 significant digits would have to have this 9b subtracted from it. That requires borrows and all sorts of complexity. And if we were actually to do this in a computer, it would require us to have this entire number put into a single register of the computer before we could start figuring out how many times that goes into the dividend, how many times the divisor goes into the dividend, and figure out what our remainder is. Turns out there's a much simpler way. We covered this in the CRC video, what we do is instead we grab as many significant digits in our dividend as we have significant digits in our divisor and do a borrowless subtract. So I'm going to take this 1001, 1011, and subtract it from that so from those bits in the dividend. But notice that without borrows, what I can do is I can pull a 1 out of a 0, assume that we have a borrow from the previous column. We're not going to perform the borrow. But if I did have a borrow from the previous column, I'd have a 1, 0 minus 1. 2 minus 1 is 1. 2 minus 1 is 1. 0 minus 0 is 0. 2 minus 1 is 1. 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 1 is 0. And what I've done is performed a subtract without borrows. And this makes it so that instead of requiring the whole number to be in a register of the processor before I start doing the division, all I need to do is have a window that slides along until I have a 1 in the most significant bit position that matches the 1 in the most significant bit position of the divisor. Notice that whenever I do that, what I'm getting always as a result in this most significant bit position is always a 0. This 0 means that the result of any borrowless subtraction is always going to have 1 fewer bits, at least 1 fewer bits than the divisor. So after I do this long division, the remainder that I'm going to get at the bottom is going to have 7 bits because my divisor has 8 bits. So let's keep doing this division. What I'm going to do is I need to pull down enough bits from here in order to make it so that I've got a 1 in the most significant bit of the value from the dividend that I'm subtracting the divisor from. So that requires 4 bits. I've got 4 bits here, so I pull down 4 more bits, 1, 1, 0, 1. I take my divisor, 1, 0, 0, 1, 1, 0, 1, 1. And by the way, real quick, forgot to mention this, very important, that if you look, if the bits are different, I'm going to result in a 1. If the bits are the same, I'm going to result in a 0. Same, 0, different, 1. This borrowless subtraction really is a bitwise exclusive OR. So this operation that we're doing here is a bitwise exclusive OR. Now, if you look at the bitwise exclusive OR, when there's 2 inputs to an exclusive OR, if they're the same, the result is 0. If they're different, the output is a 1. So I've got same, 0, different, 1, different, 1, same, 0, same, 0, different, 1, same, 0, same, 0. Now, this means that I require 2 bits to be dropped down from my dividend to make it so I have 8 bits that I'm subtracting my divisor from. So I drop the next 2 values down, take my divisor, 1, 0, 0, 1, 1, 0, 1, 1, do a bitwise exclusive OR. I've got different, 1, same, 0, same, 0, same, 0, and so forth. All right. And then I have to also drop this last one down. Didn't get enough bits in order to make it so that I have the same number of bits in my divisor as I have significant bits and values that I'm subtracting from. So this right here is our remainder. Now, that's not quite the way entirely that a CRC works, because if you look at it this way, let's go ahead and add a couple of numbers. How about I'm going to just take a little bit of room down here on the board, and I'm going to add a binary number. We'll just simply say 1, 1, 1. All right. And if I add those together, I've got 0 plus 1 is 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. Now, if I were to do this addition exactly the same, do this exact same addition again, except this time instead ignore any carries. In other words, have a carryless addition, what do I get? 0 plus 1 is 1. 1 plus 1 is 0. Don't worry about the carry. 0 plus 1 is 1. 1 plus 1 is 0. Don't worry about the carry. Guess what? This looks exactly like that borrow less subtract. It is, once again, an exclusive OR operation. So that actually gives us a tool to use whenever it comes to implementing CRCs. Because if we take the CRC, the result of the CRC, and say, okay, my borrow less subtract is exactly the same as a carry less add. If I take this value, this remainder, and I add it into the value, the dividend up here, if I add it, that's exactly the same as subtracting it. All right, follow me for a second here. Taking this result, this kind of pseudo modulo, and adding it into the value that I had for my dividend, that's the same as subtracting it. Well, if it's the same as subtracting it, then wouldn't that be the same as pulling the remainder out of the dividend? And if I pull the remainder out of the dividend, then that will actually give me a number that's divisible by the divisor. Try that one more time. Let's just say that I have 10 up here, the number 10, and I'm dividing it by 3. Well, I divide it by 3, I get 3, but I have a remainder of 1. If I pull that 1 out of the 10, the result I get is 9, which is divisible by 3. So you get the idea. Well, all I'm looking to do is take this remainder right here and pull it out of my value. If I send that along, then the receiver, whenever it does exactly the same division, it should get a result, a modulo of 0. But I don't want to take this data and modify it. I don't want to say, okay, here's my data, and I'm going to, by the way, pull this remainder out of it. I'm going to modify the data. So what I do is I take zeros and I add or append to the end of my number here some zeros. And by appending to my number some zeros, what I've done is made a place to put or add the remainder. If I add the remainder in this location right here, then adding the remainder in that location will be the same as subtracting the remainder. And then whenever I pass this whole message here with the modulo inserted where these zeros are, then whenever I do the long division on the receiving end, I should get a remainder of 0. Let's show you how that works. This value, this 7-bit value here, is the modulo of this dividend, including the zeros, the 7 zeros appended to the end, divided by this divisor, 9b in hexadecimal. So what I'm looking to do is now the sender, after performing this and getting this modulo, it is going to substitute that modulo in for these last 7 bits. So I put those 7 bits, take those zeros out, I put 10000001 in this modulo, this result of the modulo right there. All I've done really is I've added it in. Remember, adding is the same as subtracting whenever we're talking about these carryless adds, these carryless additions and these borrowless subtractions. So really what I've done is I've subtracted this from the dividend. Now, if I perform exactly that same division, we should get a result of 0. Let's see if it works. And we've done it. Notice that by changing this to those last 7 bits, by adding in or subtracting the modulo from the original division and putting it in those last 7 bits, I get a result of 0. So the receiving device, it simply has the same divisor, but this time now it's received its string with the last bits, those last 7 bits of zeros, 1 bit fewer than the number of bits for my divisor. If I have that modulo result substituted in there, when I, as a receiver, start doing this division, I will always get a result of 0. So here's that same division, cleaned up a little bit so you can see how things line up. We've got the capital H, we've got the lowercase I, and we've got the modulo, those three pieces in there. What we're looking for, though, is, remember, the problem was when we used a datasum-based checksum, that if the least significant bit on the H turned from a 0 to a 1, and the least significant bit on the lowercase I changed from a 1 to a 0, we found in the datasum that caused that we still got the same result, like everything was okay. Let's do it in this long division and see what happens. When we make those changes, and you can see that as it propagates through to the final result, our final result is going to not be equal to 0. Hence an error. This is the beauty of the CRC. Any bit change changes things enough or radically enough in the result so that it's very hard to have an equal and opposite error to correct it. Another way of looking at an exclusive OR is it's kind of like a programmable inverter. Let's talk about it this way. If I make the truth table for the exclusive OR, so I have A exclusive ORed with B, and there's my full truth table. If they're the same, the result is a 0. If they're different, the result is 1. Now, notice another way of looking at this is that if A is equal to a 0, B is just passed straight through. It's like there was no change at all. It's like the device wasn't even there. If A is set to a 1, what we're looking at is the value of B gets flipped or inverted. We can look at the application of the bitwise exclusive OR in our long division in exactly the same way. What we can say is that if the most significant bit of the bits that we've pulled in from our dividend is equal to a 0, we're not going to do the bitwise exclusive OR. Hence, the A is equal to 0. We're not going to make any modifications whatsoever. If, however, the most significant bit of the bits that we're shifting through in this long division in our dividend, if that most significant bit is a 1, then certain positions are going to be inverted. That's really all we're doing with this long division. Let's see what it looks like whenever we actually do it with the long division we've been performing up to now. Now, aren't you glad I didn't start out with this one? You can see with this long division here that as you go through, we are either not doing a bitwise exclusive OR or we are doing a bitwise exclusive OR, all based on whether that most significant bit of the bits from the dividend is equal to a 1 or it's equal to a 0. If it's equal to a 0, we're just doing a bitwise exclusive OR with all zeros. If it is equal to a 1, then we're doing a bitwise exclusive OR with those certain positions set to 1. In those positions, note that it's going to invert the value that we had pulled down in our long division. So really what we're looking at is a shift register. So I've got this shift register. It's going to be an 8-bit shift register. All right, so I've got an 8-bit shift register. And what's being shifted in, and my apologies right up front for showing you exactly the way we've been doing it before. We shift in to our D and out of our Q. And so these bits, as they are getting shifted along, very much act like the bits that are shifting along in our long division. And I probably should put the clock here. It's getting sloppy because I'm trying to be quick. All right. So imagine that our bit stream is coming in from this direction. So the first bit comes in, it goes into this first flip-flop. Then the next bit comes in, it goes into the flip-flop. And the next bit comes in, and it goes to the flip-flop. And the next bit comes in, and so forth. Until we get to the point where the first bit of our bit stream is in this most significant bit position. Now remember, what are we looking for? What we were looking for is when a 1 is in here, we invert certain bits there. All right, that's all that our long division is doing. So when a 1 is in here, certain bit positions are going to get inverted. Now remember that after our long division, after our bitwise exclusive OR, the value that is here is always being exclusive ORed with itself. So whatever is coming out of here is going to get shifted out as a 0. But what's in there at the moment, that is going to be brought around to be inverting certain ones of these positions. Let me try that again because I don't know that that came out quite right. So the number is coming in from our bit stream. So this is our input, our bit stream that's being sent to the receiving device. As those bits come in, as soon as a 1 gets in this position, I want to perform that bitwise exclusive OR with certain positions. After I perform that bitwise exclusive OR, we're going to shift over by 1. Well, why don't we skip over the step and just do the bitwise exclusive OR and the shift at exactly the same time? Well, what that's going to do is we are going to get a bitwise exclusive OR here, right? A bitwise exclusive OR here. I'm just identifying the points at which we were doing the bitwise exclusive OR before. I'm going to skip that one. We'll do a bitwise exclusive OR here. This is really getting tight. That's supposed to be a bitwise exclusive OR. And actually, no, when I say bitwise exclusive OR, I apologize. These are not bitwise exclusive ORs. These are just individual exclusive ORs. And we're going to do another exclusive OR right here, which the combination of all of these is going to perform our bitwise exclusive OR. And so all the numbers come in, and notice that as long as there's a 0 here, each one of these exclusive ORs is just going to pass along the value that was in the previous flip-flop. So as long as that's a 0, this is just a shift register. And what we're doing is we're pulling in additional bits from our, dividend. And soon as there's a 1 in this position, that 1 is going to cause this bit to be inverted before going in here, this bit to go and be inverted before going into here, this bit to get inverted before going in here, and this bit to go inverted before going in there. And we get that bitwise exclusive OR. The most significant bit is always going to be a 0 after that bitwise exclusive OR. So after the shift, it just drops off. Even if there was a 1 in here, it's going to be ignored because basically what you're looking at is there would have been an exclusive OR at this position, which since we're exclusive ORing something with itself, something exclusive ORed with itself is always equal to 0. Let's draw this a little bit cleaner. All right, there you go. It's a little bit cleaner diagram than that one up there. What may be confusing to some of you is that our bit stream is coming in from the left. If our bit stream is coming in from the left, that's backwards from how we picture a long division. In a long division, our bit stream was coming in from the right. So if we switch this around, you can actually hopefully see how the bits will come in from our stream on the right-hand side. As soon as a 1 gets in this most significant bit position, we then do the bitwise exclusive OR with those individual positions as we do the shift, and then that basically brings us to the next level where we're going to decide whether or not to do a bitwise exclusive OR. On the receiving end and on the transmitting end, you have this same circuit because remember that our divisor defines where those exclusive ORs are. So on the transmitting end, what you're looking at is this same circuit. This circuit gets driven through with the zeros as tacked onto the end where we're going to put the remainder. As soon as we generate that remainder, that gets substituted in where those zeros are, the whole thing goes out the door. Now on the receiver end side, you're going to receive each one of those bits into this shift register, and once you've received the whole message, including the modulo, the value that should be in all those flip-flops should be 0. In our next episode, what we're going to do is see how LFSRs might be used to correct errors, not just detect them. Until then, remember that while the scope of what makes a computer is immense, it's still all just 1s and 0s.